Let's talk about how much energy we can store in springs. There's some renewable energy work going on about compressing air to store energy, and then when you need the energy back, you let it expand and turn a generator. So we're going to focus on a simpler question about how much work does it take to compress a spring some distance, and we could even ask a nice mathematical direct proportion kind of question. Does it take twice as much work to compress it or stretch it twice as much? So I thought we'd have a fun little demonstration here. So here's an empty water bottle with some holes in it and a spring. And I've got some dominoes here, 17 grams each. So we can put those in. Well, first we'd want to, before we put the dominoes in, we'd want to measure what the rest distance of the rubber band is. And then as we add more and more dominoes, measure how far it gets stretched every single time. So I'm not going to bore you with that already. Right now I've actually done that already. Let me show you a few clips of the video. All right, we've got our measuring tape there, and I'm just going to skip through a little bit here, except it's not working. There you go. So me and my little research assistants were working on this. We actually did 2 rounds of data. Took us 30 minutes. You can see the final data collection thing somewhere at the end here. There we go.
All right.
Okay, so let's go look at the resulting spreadsheet. So we had 2 rounds of data taking, and we'd add a domino each time and measure how far it was, and then you can compute how far it is beyond the rest length. So I've got the round 1 in blue, round 2 in orange, and here's the graph we get saying based on how many dominoes are in the water bottle, how far was the spring or the rubber band stretched beyond its rest length. This is an interesting graph to think about. It's looking like the differences between round 1 and round 2 weren't just random, they were kind of systematic. I had pre-stretched the rubber band, so I don't think it's because the rubber band is getting more and more stretched as we go along. I don't think that's a big factor. Maybe I was eyeballing it systematically differently. I don't really know. This is pretty clearly a slight nonlinear pattern, but I think we would all be reasonably happy if we approximated it with a straight line. We could even group the 2 sets of data together and approximate that with a straight line. There's something called Hooke's law, which says there's a straight line relationship, direct proportion relationship between the weight on a spring, or the force you're using, that's the force you're using, and how far it's stretched or compressed beyond its rest length. So we see Hooke's law isn't exactly right here, but maybe it's close enough to write for a first approximation. But here's what I want to do. I want to change our thinking from based on how much weight I put on it, how much stretch do I get? I want to flip it around and think about, as I stretch it more and more, how much force is it taking to keep it stretched that much? So it's the same data as this, but just with the x and y axes flipped and a different interpretation, saying for any particular amount of stretch, how much force is it taking to do that? And we see this relationship, y equals 0.9127x. So that's x is in centimeters and y is in force or number of dominoes or whatever. So that's what we're going to use when we get back to paper and pencil. So we got data, when we took it, it went like this. We were increasing the weight and saw the amount of stretch increase. Here's a good question. Is that a good statistical design to systematically increase the weight and see the amount of stretch increase? Or should you try different weights in a random order rather than strictly increasing? Come take stats with me and we'll talk about that, or send me an email. But then we said, let's think about it the other way. Based on the amount of stretch we're seeing, how much force does it take? Or how much force is the spring giving us? And we saw a graph like this. It wasn't quite linear, but it was pretty close to linear. So when this was first discovered, I think Hooke has an E in there. Hooke's law is that the force is directly proportional to the amount of stretch or compression, which is what this is saying. And our data showed it's roughly true. So let's get back to this question of how much work does it take to stretch or compress a spring some distance. Let's say how much work will it take to stretch the spring 4 centimeters from its rest length. And now we're supposing that there's no weight in the bottle. I'm just using my own force to push down on it, and the spring is pulling back. And the problem is, you might say, well, let's just use work equals force times distance, but the force is not constant. Every time I push a little bit more, the spring is pulling back with even more force. So I can't just say, take whatever force it is and multiply by 4 centimeters, because it's a different force at the very beginning and then in the middle and the end. So let's deal with that in the next video.